Hello again, everybody. This is our video solution to problem 14b from the fall 2020 Math 210 final. We are sticking with series, and here, instead of radius and interval of convergence of a power series, we just have straight series, and we want to know whether or not they converge or diverge. So we have three examples. And the first thing I want to do is just go through and say, like, how do we intuitively figure out what these are supposed to be? So let's look at number one. I ignore constants, right? So I see a 5 here, and I just don't care, right? Think of this as a 1 over, and then the n minus 2. I don't care about the minus 2. In my brain, I'm thinking this is 1 over n. 1 over n, we know that that's the harmonic series. Yeah, we're missing a couple terms from the beginning, but those don't matter, right? We only care about the tail anyway. So this thing should diverge. I look at the second one. Look, I have a nice rational function of n. I go to the highest powers. Look, they're both n squared, right? Which means this sequence, the underlying sequence, converges to 3/7. Yeah, there's no way this thing is going to converge, right? Individual sequence is not converging to 0. So the series has to diverge, right? You're basically adding up a bunch of 3/7 forever. No way. Okay, let's look at the last one. Well, this looks like the first one, right? You have this 5 over n minus 2. I ignore the 5. I ignore the minus 2. So it's basically 1 over n. But there's an alternator. So this is the alternating harmonic series. So this thing should converge. Okay, so in a minute and a half, I basically can work out the answer to all three of these things. Now let's write in the details. So for this first one, right, we should again be thinking this is basically the harmonic series. So we're going to want to use the limit comparison test. So I say, okay, let's see. 5 over n minus 2, I claim that that sequence is asymptotically equivalent to the sequence 1 over n. So how am I going to prove this? Well, limit comparison test says I need to look at the ratio. 5 over n minus 2 times n over 1, and then I take the limit as n goes to infinity. All right, well, how about I pull an n out of this piece here? So if I pull an n out, I get 5 over, and I'm going to put the n right over here, and I'm left with 1 minus 2 over n. Now this n over n, this is just equal to 1. And now what happens here? 2 over n, that goes to 0. So 1 minus 2 over n goes to 1. 5 over 1 minus 2 over n goes to 5 over 1. So this limit is equal to 5, which is a positive constant. So hey, we're right. These two sequences are asymptotically equivalent. And so this implies that the series starting at 3, 5 over n minus 2, converges if and only if the series starting at 3, 1 over n converges. But this is the harmonic series. Yeah, again, minus the first couple terms, right? But this is essentially the harmonic series. And it diverges. So we conclude that this series diverges. All right, second one, okay, we know what the argument is supposed to be, right? We want to show by the non-vanishing sequence test, this sequence converges to 3/7, and so the series diverges. So let's take a peek. If I have 3n squared minus 4n plus 5 over 7n squared plus 6n plus 4, I factor out an n squared, and I get 3 minus 4 over n plus 5 over n squared over n squared times 7 plus 6 over n plus 4 over n squared. And as n goes to infinity, 4 over n goes to 0, 5 over n squared goes to 0, 6 over n goes to 0, 4 over n squared goes to 0. Of course, these n squareds cancel. And so as n goes to infinity, this sequence goes to 3 over 7, right? The only thing that doesn't go to 0 here. All right, but again, if your underlying sequence does not converge to 0, then your series diverges. Okay, so this diverges by the non-vanishing sequence test. All right, finally, we have this alternating version of the original series. Okay, it's not quite the original series because, oh, it says it starts at 1, but of course that should be a 3, right? That's just a typo. Okay, so yeah, I mean, we would have a pretty serious problem when n is equal to 2, right? You'd be kicking a puppy, and we don't do that. All right, so we want to use the alternating series test here. So in order to use the alternating series test, we have to check the hypotheses. What are the hypotheses for the alternating series test? Well, we need that the underlying sequence without the alternator, right? So here, alternating series test. We need that 5 over n minus 2, so without the alternator, is eventually decreasing and converges to 0. All right, well, it's easy to see as n goes to infinity, this goes to 0, right? That's not a problem. How about the eventually decreasing part? Well, again, as n is increasing, right? So n increasing implies n minus 2 is increasing. But that implies that 1 over n minus 2 is decreasing because you're looking at the reciprocal. The bigger you make n, the smaller the fraction gets. And of course, that implies that 5 over n minus 2 is decreasing. So for n at least 3, this fraction is always decreasing. So we can use the alternating series test, which amazingly just says you're in this situation, you have an alternator, you have an alternating series with these eventually decreasing and converging to 0 properties, and this just automatically converges by the alternating series test. All right, there we go. We've nutted through a bunch of series. We'll see you next time.